We did some graphing of motion. You did some graphing of motion in your lab. And you noticed some things. So what are the axes on your graph? Give me one, Brady.
Like X or Y? Or
Well, we know they're X and Y, but what is... Okay, so I'm going to put time. I'm going to use time that you just gave me. So time, and you all had it in seconds. Time, in any case where we're graphing something and time is always going to be your x-axis because time is independent. Time marches on. Time does not care what you think about that. Time keeps going regardless of what you have to say about it. Trust me, that'll become more and more evident to you the longer you spend on Earth. So time is always on the x. I'm going to pick on somebody else. What was your y-axis on your first set of graphs? Be careful here. You might suspect that this is a trick question. Position. Excellent. Position. And there are three kinds of graphs that we're going to talk about when we talk about basic motion. The first of them is a position time graph, is what we typically call this. So we have time, and again, we said here it's in seconds. So starting at, second 0, we have some point in time, and then 2, 3, 4, 5, we have some point, and we could say this is in meters, but it could be in anything. It could be in feet, it could be in kilometers, it could be in centimeters, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. So if we have an object, let me ask you this. On a position time graph, does your object necessarily have to start out at 0 position at 0 seconds? Nope. Doesn't have to. Now, in your case, it did, and we very commonly handle graphs where it does. You could start off at 0 seconds at your 5 meter mark. There's no telling where you're going to start. Also remember that those 5 meter marks, 10 meter marks, 1 meter marks, centimeter marks, whatever, are arbitrary. We're imposing a grid system on the whole world, because that's what we do, mathematical little primates that we are. So what if my object starts there, and I measure its position at the 2 meter mark, and it's there, and at the 3 meter mark, it's there, and at the 4 meter mark, it's there, and at the 5 meter mark, it's there, and at, 2, 4, 6, 8 meter mark, okay, and at the 10 meter mark, it's there, and at the 12 meter mark, it's there, and at the 13 meter mark, it's there. So tell one another, don't tell me just yet, describe to one another what's happening with this object. Okay, how many of you said something like it moved for a while, then it stopped? Okay. So you all recognize that if the position is not changing in some time interval, this object is not moving. It has come to a stop. If it's a car, it parked. During this portion of the event, it was moving. So let me ask you a question. I must ask you a question. I'm going to get rid of these. Comparing this object to an object that started also at the 5 meter mark, but at the 2 meter mark was only there, oops, and at the 4 meter mark was only there, and at the 6 meter mark was only there, and at the 7 meter mark was only there, and at the 8 meter mark, I mean, you get where this is going, I think. What is the difference in those two objects' motion? Talk to one another, not to me. Don't yell it out. I heard a few people say words like faster and slower. One object is traveling faster than the other. One object is traveling slower than the other. And you pretty much know this intuitively. And I don't know how much of this you had in physical science. I don't know how much of your freshman year you remember. It's been a while. But how many of you would agree that this object is moving faster and this object is moving slower? Okay. But how do you know that? So you're saying that the time it takes the faster car to get to the same position is less than that of the slower car. Okay? Do we want to add to that? Subtract from that? Challenge that? You want to add, argue, subtract?
Just adding.
Okay.
The faster car, the position increases a lot more per second than the slower car.
Okay. Oh, you're saying like the rate of increase in position.
Yeah.
Interesting. So you guys are doing a really good job attaching reason to this, because what you're all intuitively seeing is something inherent in the lines. What is different about these two lines if you have to describe that? Slope. Huh. Oh, you just got it. I love it when I see little light bulbs twinkle out there. It's so much fun. It's like a Christmas tree lighting up. So the slope of these lines is different. Well, position, change in position. What else do we call that? We call that, we call that delta x, because we're all talking about the x-axis here. And what this is time, so that would be delta t. What's our equation for velocity, average velocity? Delta x over delta t. Oh, that's peculiar. You could almost find the velocity by looking... Well, wait. So slope of the line equals delta y over delta x equals... And velocity is equal to delta x over... Oh, and here... Slope of the line gives you velocity. Pretty slick, isn't it? I likes it. So when you find the slope of a line on a position time graph, what you are getting out of that is the velocity. Now, let me ask you a few more probing questions about these lines. What is true of the slope of each of them, barring my terrible drawing? And we're looking for a line of best fit here. There, that's better. They're linear. Therefore, the slope is constant. Slope's constant. These are straight lines. So what does that tell us about the velocity? It's constant. These are objects moving with constant velocity. So when we see a straight line on a position time graph, we know we have an object moving with constant velocity. Now, there's something else we can tell about the slope of these lines. Let me give you a line to compare it to. What is true about the slope of the first two lines? Positive or negative? Positive. Slope of the blue line? Negative. So the first two objects have got positive or negative velocity? Positive. Now remember, we can have positive or negative velocity because we're thinking about everything in terms of being tied to a railroad track. And if your final position has a greater magnitude than your initial position, xf minus xi, then velocity is going to be positive. What if we have a negative position? Can you do that? Yeah, because it's arbitrary. We've decided to take this Cartesian coordinate system and slap it on the world. Now, if we are, depending on how, I don't know, what would you say, brainwashed, assimilated, be the Borg, depending on how brainwashed or assimilated or whatever else we are, if you tend to look at the world as this Cartesian coordinate system, then you would, and now those of you who know me know I can't do left and right. This is my right hand, so that's right? Okay. Yeah. So if you're seeing that Cartesian coordinate system imposed on the world, you would tend to think in these terms. Or if, like me, you prefer the cardinal directions to orient yourself in the world, you would tend to see west as negative numbers, east as positive position numbers. We'll get to the north-south axis, the y-axis, in terms of position a little bit later. But we would tend to see that if we are imposing the Cartesian coordinate system on the world. Again, it's arbitrary. We made it up. But it doesn't. So what if your initial position is -5 meters from whatever your origin is, and your final position is -1? What's your displacement? What's your change in position? -1 minus -5. Is that a positive or a negative? Positive. Positive change in position. Well, okay, we'll leave that alone for a moment. And this is everything that we've just said. When you plot position time, you're actually getting a velocity out of the slope. So it's fairly convenient. Average velocity is slope of the line, and we looked at a couple of lines that had constant slope. You can put a dot on either end of this. Boom, boom. You can find the rise over run. You can find the delta y over delta x. You can get a slope. That's very good. That's wonderful. Time in seconds, position in meters, and let's look at an object that does something like this. Okay. So, talk to one another and explain what's happening here. Okay, so I'm hearing good murmurs and rustlings and whispers, and I'm hearing words like speeding up, and then I'm hearing constant and slowing down and stuff like that. So what we have here is an object that is slowly speeding up during this phase of its travel. Its rate of speed, the slope of that line is increasing. You're going from a very low slope, almost a zero slope, in the first couple of seconds to an increasing slope. And then we have a relatively constant slope here, and then that curve of slope starts to change here, and the slope decreases. So there are a couple points, somewhere from maybe like here to here. We might have a segment with constant slope. But then it changes, it tails off, and again here we might have a constant slope. So we sort of turn a corner here. Looks like we kind of turn a corner here. The slope is not all that far off constant in this section. Can you think of an object that would behave this way? Car. Under what circumstances?
Going in a very straight line.
Well, this is all straight line because this is all one axis. But think about its speed behavior. I would hope not. I would very much hope not, because you'll probably die. I'm going to say this is stop and go traffic. So you speed up, and then you're starting to slow down again, because remember, the slope of the line is your velocity, not how high the line is, not the magnitude. And you were one step ahead, so you hold that thought, because we're going to get there. We're just not there yet. We'll get there like Monday. So let me get rid of all this extra junk here. So here we have someone who's slowly speeding up, coming off a stop sign or a stoplight. They get it up to some rate of relatively constant speed. The light ahead of them just changed. They start to slow down. Now, if we see that next, they're stopped. Their position is not changing. What would it look like to draw a line for somebody merging onto a highway?
Go up again.
I'm going to suggest that depending on what you're driving and how leaden a foot you have, so I want you to imagine this. I would draw it. I'm going to draw it, and then you guys can argue with me and pick on me and tell me if you think I'm wrong. Okay. Is there anything wrong with that? There might be. It's entirely possible.
You're going faster merging onto the highway.
Okay, so you really gun it on the ramp.
Yeah.
Like really gun it. That's probably not actually possible for most vehicles. Let me revise that.
80 on the ramp, 70 on the highway.
Well, you know what? Have any of you ever gone to Pittsburgh via Beaver Falls on the Pennsylvania Turnpike?
Yeah.
The merge ramp where you get on 18 right by Giuseppe's, that's an amazing little Italian restaurant, by the way. Get on by Giuseppe's and you merge going over the bridge over the Beaver River, and then you go up the big hill. Have you done this?
Mm-hmm.
You have homework. You have homework. So yeah, hop in your car, take a few friends. Don't die, please. And the ramp, and my husband is a native Pennsylvanian. I have complained to him about this many, many times, though he had nothing to do with it. In the state of Pennsylvania, they do not believe in giving you more than about, 50 meters to merge. 50 meters, 4 lanes, you got to cross 4 of them. Oh, by the way, there's a bridge and a river and a cliff. Make it work, people. Driving in Pennsylvania.
One bridge in Pittsburgh where there's 4 lanes.
Okay, so let's try this again. So, but you have to hit that rate of increase pretty fast, and then you may stay at a pretty similar velocity. Generally, you want to try to be up to about 65 by the time you get off the end of that 50-foot ramp. It's really ugly. Yeah, I can't assign you homework there in good conscience. But it's, that would be somebody accelerating really hard and then really quickly achieving their constant velocity. What are some other scenarios? Do you have questions on this? Okay. So now let's look at this. So when we see an object whose velocity is changing, our position time line is curved. And you should have seen this with the marble or the bouncy ball or whatever the heck you rolled down the track. Your position time, I'm giving this away, but now you know that if your position timeline is not curved, you should probably go back and revisit your graph. Your position timeline is going to be curved because that thing is changing its velocity. Now, knowing what you know about gravity and how things move and rolling down hills, perhaps some of you have thrown yourselves down hills on slightly lubricated objects under snowy conditions. Yes? Excellent. It's one of my favorite winter pastimes. I do make my daughter wear a helmet, though, after that one time. So when you are going down a hill, when a ball is going down a ramp, what are we going to see in that line? Are we going to see this, or are we going to see this? We'll call this A. We'll call this B. Something that is speeding up going down a hill. B. Yeah. The velocity, the slope starts off low, increases. What's a scenario for A? I know one for me. That's me pedaling my bike up a hill. I always try to get a good head of steam at the base of the hill. I try to hit that hill with as much velocity as I possibly can. Invariably, gravity wins. And by the top of the hill, if I'm still on the bike, I'm very lucky. Yeah. So, okay, you understand the slopes of the lines. When we have an object whose velocity is changing, how many of you are in calc right now? About half, usually? Okay, usually it's about half. You have not done derivatives yet, correct? You're just doing limits?
Yeah.
Okay, you're starting derivatives soon.
Yeah, next chapter.
Next chapter, okay. So, You'll understand this next chapter. When we look at this line, we can't get a slope for the whole thing because the slope changes throughout the line. What we can do, however, is take a portion of the line, a single point, and draw a line that is tangent to that point. And we can find the slope of the tangent line. And what that gives us is the velocity in that very moment. Okay? So what your, if we think back to, you know, one of these being a car, the slope of the tangent line at a given point in space is the speedometer reading. That's instantaneous velocity. We cannot find average velocity in a situation where velocity is changing. That doesn't make any sense. I mean, we can, but it's not real useful. So imagine, for instance, taking a drive. Here, you want homework? Take a drive. Go get in your car, make sure you got a few buddies and some gas money. Go to California. Yeah, sure, why not? Sure. Don't tell them I told you to. You know, or drive to Oregon. Drive to, I don't know, Iowa. Iowa's really nice, actually. You'd be surprised. Grant Wood country. It's beautiful. I like Iowa. Anyway, get in the car and go on a nice long road trip. You're probably going to want to take a potty break. Nah! Oh, my gosh. So if you're going to take a trip to wherever, Iowa, Chicago, California, I don't care where you drive. You could drive to Canada. You need a passport, but that's okay. It's beautiful there, and they have amazing food. So you're going to take some potty stops. You're going to stop and get gas. Your instantaneous velocity at some points on this trip may be 115 kilometers per hour. If we figure the amount of time it takes you to leave, if you're leaving right from the parking lot at 2:30, you can probably be in Toronto by 8 o'clock tonight. Time for dinner, late dinner. You have to be back for school tomorrow, though, so that's going to stink. Anyway, your average velocity is going to be significantly lower than that because all of those stops count against your total time. So that's what some of the problems that you've been doing have been hinting at. When you stop, that counts against your average velocity. Questions, comments, concerns? Here we have an object speeding up, attaining constant velocity, slowing down, maybe coming to a stop. We don't know what happens off the screen. Wow! Whoops. That's a position time graph. Now let's look at the next graph we're going to do, and this is where Brandon and I were both going. Now we're going to talk about what happens if we graph velocity against time. So here we have on the y-axis our velocity at any given moment. And I'm intentionally not putting in units. We're just kind of doing this conceptually. So if we look at this object here in this segment, is it moving very fast? No. Its velocity is pretty low. So we'll put a dot down here for velocity. Is its velocity increasing? Yes. When it gets to this segment, its velocity is a little higher. Is its velocity changing in that segment? No, it's pretty constant. The slope of that line segment is pretty constant. What about this segment? Is the velocity beyond that purple line changing? Yeah. How so? Increasing or decreasing? Decreasing. So the velocity here begins to change again. Now, if we expanded this graph out, and we did that, what would the velocity be at that last dot? Last two dots, actually. By golly, it's 0. What? So roughly the same object, very different looking graphs. So here we have a segment where the velocity is increasing, and I actually didn't draw that as well as I wanted to. I drew that pretty badly, actually. That's what I get. Okay, we'll do that. There's velocity, there's velocity. Now, somebody had said something about rate of something, rate of change of position, velocity. How fast you change your position. How long it takes you to change your position by a certain amount. Here, we're not changing our position. I mean, we are, but what's changing? Velocity. So this is V, this is T. So we're changing our velocity. What would the slope of this line be, just in terms of positive, negative, constant, variable? Talk to one another.
Yes.
It's a positive slope. It looks to be about 1, honestly, to me, just at a badly drawn 1 off. So it's a positive slope. It's a constant slope. If we wrote an equation for the slope of that line, what would that look like? No! That's the equation for the line. Don't go there. Equation for the slope. So slope equals delta y over delta x. And in this case, delta y, or y is v, is velocity. So that would be delta v, and what's our x-axis value? Delta t. So the slope of this line gives us the change in velocity over time. How fast this object is changing its velocity. Oh, okay. Well, that's nice. What's the slope of this segment of the line? Talk to one another. Barring inconsistencies in drawing. It should be 0, yes? We agree? Should be, oh, stop it. 0.000, yeah, whatever. It should be a 0 slope. So, turns out, what we're doing there is looking at acceleration. Acceleration is how fast your velocity, it's the rate of change of velocity. How much your velocity changes in some time interval. And I very intentionally want you to scribble that out because we're going to make it intensely more complicated. Yay. And weirder and more wonderful than you could possibly imagine. We'll talk about it tomorrow. Work on that worksheet.